Hi, I'm Kavya, and this is my lab 2 for physics. And this experiment is about the velocity of a falling object. The purpose of this lab is to create an experimental model of an object falling at a changing velocity, to analyze the motion and compare this movement to two computational models, one with drag and one without, to analyze the forces at play when an object is falling. This experiment uses the fundamental principle of Newton's second law. It uses Newton's second law because the net forces acting upon the object falling do not cancel out, and the forces acting upon it come from different directions. The net force causes a change in acceleration. And an object falling doesn't have a constant velocity as both gravitational force and drag force are at play, so thus the velocity is not constant and an acceleration is caused. So the equations we're using is F equals ma, or F net over mass equals acceleration, the drag force, the gravitational force, and then also both the position and velocity update formulas. So in this experiment, the system is the falling object, in this case a paper ball, and the surroundings are the external forces on the object, so gravitational force and drag force. The initial conditions are time equals 0 seconds, position equals negative 0.007 in the y-axis, and then a mass of 0.025 kilograms. It's in the y-axis because the object is falling down. And then the lab showed how an object falling down does not have a constant velocity and demonstrates the effective drag force upon a falling object by comparing the experimental model with one computational model that accounts for drag and one that does not. So the procedure was to film a clip of the falling object and then upload a video into Tracker to create the experimental model of the position of the paper over time, and then using the code create two computational models, one with drag and one without, and then to graph them all to compare them. So for Tracker, I used a video of dropping a cardboard piece of paper, and then as I imported it, it turned sideways, so I just changed the axis of rotation. And as you can see, it gives you a position time graph that curves downwards and is not constant velocity. And then it also gives us values for the time and the position, which we can use to create our graphs. And then for the code, for the model without drag, we set the mass of the ball to be 0.025 kilograms, the initial position to be negative 0.007, because that was what was in the video, and then a delta t of 0.033, because that was also in the video. And then g, the acceleration due to gravity, is 9.8, because that is a constant. And then we leave b as 0 because this one doesn't have a drag. And as you can see, the graph also is curving downwards and is not constant, so the position versus time is changing. And then the computational model with drag, we have to set a b value of 0.0865, which we got from the equations used. And then we also set w, fd, and f net equal to different things to be able to calculate the model with drag, as you can see in the code over here. And this one results in a more linear position versus time graph, but definitely the velocity still isn't constant, as you can see. And we also get free body diagrams to this code, so you can see the difference between with drag and without the arrows that are at play on the diagram. So comparing all the three graphs, you can see that the computational model really accurately represented the experimental model, but the computational with drag did. And then the one without drag reaches a slower velocity a lot quicker because it doesn't account for the other force at play. And then some sources of error are other forces in the system, which we didn't account for, as well as inconsistent tracking on Tracker. So given our graphs, we can see that the computational model that accounts for drag force predicts a terminal velocity, and a terminal velocity occurs when the drag force is equal to the gravitational force. Thus, there will be a net force of 0, so no acceleration and a constant speed at that time. And this graph shows that the velocity is decreasing over time, and eventually the drag force will equal the gravitational force, resulting in an F net of 0 newtons, which is the terminal velocity. And if the object was thrown downwards, then the terminal velocity would remain the same as if it fell from rest, because the terminal velocity is not dependent on the initial velocity, but rather when the net force equals 0. However, the terminal velocity would occur earlier because the point at which the gravitational force and drag force cancel each other out would happen earlier due to the greater drag if it was thrown downwards. Thank you so much for listening to this lab.